morning. I am M V Krishna Rao, professor working in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Hyderabad. Here, today, I am going to start a lecture series on signals and systems. So, as you know, the signals and systems is the first course for an electronics and communication engineer to start with, and based on this signals and systems course, almost each and every course is based on, and if you want to understand any communication subjects or signal processing subject or radar, so etc., all next level courses are based on the understanding of signals and systems, and it is very, very important for an electronics and communication engineer. And probability theory and stochastic processes is also dependent on this. So you can say that this is the basic course which we cannot discard. Okay, that is the importance of the signals and systems. And before that, so I will start with the lecture 1, that is vectors and signals. So what is a vector and what is a signal? So why we are talking about vectors and signals is basically we talk about electrical signals, and vectors means a mathematical framework. It is a mathematical branch. So basically these two are remarkably similar because the signal processing engineer or systems engineer basically uses the vector analysis for continuing the analysis of the signal, that is to carry out the signal analysis. Okay, so that is the reason these two are very much linked, at least at introductory stage. Later you can discard the vector analysis and you can independently go ahead with the signals, but to start with you require the vector analysis to start the signal analysis. Okay, so let us move on to the lecture now. So this is two-dimensional Cartesian coordinate system. I am showing here x-axis and I am showing here y-axis, and I am showing a point here in this plane a comma b. That means this point has an x coordinate a and y coordinate b. So this is the point. What I am doing here, this is the origin 0, 0, 0. So from this point to this point, I am drawing a line and I am putting an arrow here. So as you know, by this time, so this is nothing but a vector drawn from the origin to the point which I am interested in, any point in the plane. So here I am considered a point here, that is a comma b, and the vector name is b. So sorry, the vector name is f. So this is the vector I am showing here, and the vector, if you see here, the vector is specified by its magnitude and direction. So what is the magnitude here? This is the magnitude. So basically this is the magnitude, and how you get this magnitude? Form a right angle triangle like this, and these are the two sides a and b, and this is the length of the vector, that is hypotenuse of the right angle triangle. So as you know, it is nothing but square root of a square plus b square. So that is what I have written here. See here. So I am representing the length of the vector f. Length of the vector f as modulus of f. Okay, modulus of f means magnitude of or length of the vector f. That is nothing but square root of a square plus b square. And similarly, I have taken another point here, d comma g. That means the x coordinate is d and y coordinate is g. So this is the point dz, and I am drawing a vector from the origin to this point dz. And I am showing this with a color red here, and I am calling this as a vector x, small x. Here it is small f, small x. Okay, so don't confuse this x with this capital X. This capital X I am using to represent the horizontal axis, and capital Y I am representing to represent the vertical axis. Okay, these two are different. So here it is a boldface, emphasized x in red color. So this is what is the vector here. And what is the length of this vector? This is from here to here, it is a d square plus g square, and take the square root. So that is how you got this, the modulus of x, length of the vector x equal to square root of d square plus g square. Okay. Now let us form, because I have taken two vectors now, and the angle between these two vectors is theta. Of course, theta I have not shown it here. So what I have to do, it is nothing but your theta. This is theta. So this theta, and so this is the theta, and the angle between the first vector and second vector is nothing but theta here. And I am forming the scalar product of the two vectors. In vector algebra, the scalar product of two vectors is defined as f dot x. F, you know, first vector, x is the second vector. F dot x, it is called the scalar product of the two vectors because the value is defined by this quantity, length of f, length of x, and cos angle between the two vectors. This is called dot product or scalar product. It is called scalar product because this quantity is a scalar quantity, like that. Okay. So now this is the scalar product or dot product I have defined, and I know the lengths of these vectors, and of course these values may not be directly useful. In that place we'll be using modulus of f, modulus of x. This is what we'll be using. Now what I am going to do is, I am trying to project this vector. This vector I am trying to project onto the vector x. So first vector I am projecting onto the vector x. So what do you mean by projection? Projection means it is the shadow of that one. For example, if I put a light here in this direction, if I sit and see in this direction, if I see, and if I put a torchlight here, the shadow of this will fall like this. Up to this it will fall. Okay. That is what. So mathematically, you can say that you draw a perpendicular to this line, which is going through this point, tip of the vector. Okay. So this is 90 degrees. Like that you should draw this. I have shown here as a black dotted line. So this is what is the point which is projecting onto this one. So what is the length of this one? This length is not full x. It is c times x. C is less than 1. For example, if the length of the x is 1, I can say that this may be 0.6. So small c may be 0.6. It is the fraction. C is nothing but the fraction of this projection compared to the full length of the x. Okay, full length means this up to this. This is full length up to this. But here I have only up to this. So this is not extending to the full length. That's why it is some part of this vector. It is spanning the part of this vector x. That's why I take this x and I multiply with some quantity c, which is less than 1. Okay. If I assume the length of this is equal to unity, a fraction, it represents a fraction. So this is what I am taking. I call this cx as the projection of f. Cx as the projection of f onto vector x. That is what I have written here. Okay. This is what I have written. On the left hand side, I have cx. Right hand side, it is equal to f cos theta. Why it is f cos theta? See, this is theta. Correct? This is theta. This is theta. And this is f. So this is f. And this length is adjacent side of this angle in the right angle triangle. So this is f into cos theta. Okay. So this is the length. So that is what I have shown. Right hand side, cx equal to f cos theta. Okay. So actually, as a vector I have shown it here. We will see later. So this is what I have again shown. Same thing I have shown here again, repetition. And in terms of vector lengths, this is a scalar quantity. I leave as it is. And I will find the length of the vector. Boldface x here. This is the vector. Its length is modulus of x. Okay. Now, this is the vector f. Take the length of this one, modulus of f and cos theta as usual. Okay. The previous equation I am expressing in terms of lengths. Now, let us multiply this equation. I can call this as equation 1. I can call this as equation 1. Multiply equation 1 by x. Okay. Now, I will get the other one. Okay. That is nothing but this. So, I have multiplied left hand side by x and right hand side also by modulus of x. Both are modulus of x. Okay. Now, x into x, x square, the length square, c into length square equal to length of f into length of x into cos theta multiplied by cos theta. So, this quantity is nothing but your scalar product, which I have defined in the previous slide. Okay. So, this is what we have. Now, C equal to this quantity in the numerator here also, and in the denominator, I am taking this quantity, correct? X bar square is in the denominator. So, this is what I have. Finally, C equal to, what is this fraction? This fraction I am expressing as the ratio of two quantities. The numerator is the dot product or scalar product of two vectors, and denominator is the length of the vector, basically square of the length of the vector. So, it is a scalar quantity. Denominator is basically a scalar quantity. It is just a scaling factor here. So, it is, basically fraction. What fraction of this is, what fraction of f? What fraction of x contains the vector f? Okay, I have the two vectors. So, I am projecting the f onto the x, and how much part of x contains f? That is the meaning of this one. How much part of, see, I will go back, see here, how much part of this is contained by this? That means f is contained in what part of the x? That is what is. Okay. The fraction of x containing the first vector f. So, that is what is here basically. Okay. This is the key aspect which we are going to discuss further in the next topics. And here same thing. This is x modulus x square. That is square of the length is nothing but x, dot product of x with itself. If I take this, then what is this? Length of x, and cos theta means cos 0. Cos 0 equal to unity. I have x modulus x into modulus x square I have. Okay. So, this is what we have. Now, let us say few things about the orthogonality. Let us define what is orthogonality. Orthogonal. If the vectors are orthogonal to each other, what is going to happen? What is orthogonal? 90 degrees. The angle between this must be 90 degrees. Theta must be equal to 90 degrees. That means pull this upwards, pull the vector f upwards, pull the vector x downwards. So, like this. See, it has gone up, still going, and here it is still going down. Okay. So that this angle, now it is almost maybe 80 degrees like that, and let us make this as 90 degrees approximately. Okay. This is approximately 90 degrees. So, what is happening here? What is the thing you have observed here? Can you just see, compare these two figures? And here it is cx, very lengthy. It is very lengthy here, and in this case the length cx is very small. Here the cx is very large. Cx is very large here. You compare these two. Okay? Compare these two. So, if you compare these two, what is happening is the fraction c is reducing. That means they are becoming more orthogonal. Orthogonal means the f, in the first case, f is contained very much inside X as a part of X. But here it is not, it is big portion is outside this. That means the vector Cx is small fraction of the whole vector X. So the F and X, they are not similar. You can say that, you can define a kind of similarity. That means the two vectors are not similar. That means as the theta increases, the similarity between the vectors, it will come down. Okay, if the theta slowly reduces, let us say it is reducing, what will happen? Theta becomes 0. When theta becomes 0, then what happens here? I have told you already, the cos 0 becomes 1. So that means when there is no angle, theta equal to 0 means F and X both are same. That means they are highly correlated. That means they are highly similar basically. Correlated means similar. Two vectors are more similar. And if theta equal to 0, two vectors are same. If theta equal to 45 degrees, the two vectors are it is not full similarity or dissimilarity. It is halfway through. Okay. And if the theta equal to 90 degrees, absolutely there is no similarity. The F and X both are totally dissimilar. There is no similarity at all. The similarity or correlation is 0. You can say that. Okay. So that is how the vector, and in future, we are going to show that this type of orthogonality concepts is very popularly used in case of functions and signals also. Okay. So I think you have understood what is a vector. So far I have defined a vector, and I have defined the length of a vector, and I have defined the scalar product of a vector, scalar product of two vectors, and I defined the orthogonality of two vectors. Okay. So far that is what I have done. Now with this little knowledge, let us move to the signals, because I am going to apply the same analysis, similar terminology I am going to use on the signals also, basically. So what is a signal? Let us see the signal as an independent thing, as an electronics engineer. So signal means here, it is an electrical signal, basically. So what is electrical signal? Any quantity, any signal. That is the reason I am saying here, you see, read the definition here. If you read the definition, you will understand very clearly. A signal is the electrical equivalent of any physical quantity. For example, in this room, I want to measure the temperature. So what I have to do? I have to keep a thermometer, and every 5 minutes, let us say I want to see what is happening, how the temperature is changing inside the room every 5 minutes, or every half an hour, every 1 hour. So I will take a paper and I will note down on the paper the readings one by one, every half an hour, let us say 3 hours successively. I want to see every half an hour. So 6 values I will get. So this is the 6 values I can in Celsius degrees or in Fahrenheit degrees I can note down. Okay. So this is physical quantity. What is that physical quantity I am measuring here? I am measuring the physical quantity, the temperature. This is the physical quantity which I am measuring. And this temperature now, because of electronics, because of the advent of electronics or electrical and electronics, so we are going to convert this physical quantity in signal domain. That means electrical domain. So I am representing, instead of writing these values on the paper, I put this to a circuit, electronic circuit, and it converts into a voltage or current. That voltage and current I will give to a galvanometer, and I can see the needle moving as per the temperature, or I can record it on the tape, or I can digitize it and I can store on a pen drive or a hard disk or any kind of media I can store. Okay. So that is the reason. That is the reason these all physical quantities nowadays, we don't directly deal with this manually. We don't deal with any of these parameters. All these parameters, temperature, pressure, speech, and electrostatic fields of in the brain, and electrostatic fields in the walls of heart, ECG, electrocardiograph, EEG, electroencephalograph. This is what is the signals which are, this is the recording technique which records the signals in our brain. So you have 64 electrodes. For example, you can have 64 electrodes you can put on your head, and at every point the voltages are measured. The voltages are in the range of microvolts, very small voltages. So you can analyze this and you can do a lot of analysis on this, what you are thinking. So are you really lying or not? Even it is so many advanced techniques have come up. Are you lying or not? So in that kind of things also possible. Okay. So why all these things is possible? Because I have converted the physical quantities into the electrical quantities. Okay. So once I convert into electrical quantities, I have a lot of flexibility there. I can magnify this. I can process this. I can change its format. I can find the frequencies in that. I can do all the things, whatever is possible. Earlier, what I was doing, I was noting down on the paper. I cannot do any analysis there, any automatic analysis. Okay, using the computer, I could not do it. Now, because of this, I'm able to convert all these physical quantities into electrical quantities. That is called signal. And what is the other thing? Pressure, for example. In the same as the temperature, you can also have the pressure measurements. And I'm not going deep into this. And speech, one is the best example of a speech. And what you use, you require a microphone. I'm speaking now. Basically, there is a microphone. Microphone is there in the camera itself, and it is recording my voice, my speech. And what is the physical parameter here? I am speaking. When I am speaking here, what is happening? My vocal cord is vibrating here, basically. Okay, my vocal cord is vibrating here, and I am pushing the air from my lungs, and it is making my vocal cords vibrate accordingly, whatever I want to say to you, and the sound is coming. It is modulated. Sound is modulated in the vocal cavity, sometimes into the nasal cavity also. And nasal cavity means nose. Okay, when you say N or M, you use the nasal cavity. When I say ah, I am only using the vocal cavity. And what is happening? Because the vocal cord is vibrating, the air particles are moving, and the sound is ejected through the lips, basically. Okay, so it is the outlet. It is like an antenna. It is like some outlet. Okay, and here the air is moving based on the pressure which I am giving. The air particles will sometimes they become dense. They come closer. Sometimes they will become wider. That means compressions and rarefactions. In physics, we know that these are called compressions and rarefactions. So these compressions and rarefactions, they are produced in the air and they reach somebody's ear. Okay. Otherwise, in our case, it is the microphone is there and it is a kind of transducer. You will say that a sensor or transducer which converts this speech. The physical quantity here, what is this? It is the compressions and rarefactions in the air. That is what is physical quantity here. So that physical quantity is converted into electrical signal using the microphone. Okay. So that is what is happening here. So this is, we are going to see some examples also in future on this. And basically the electrical quantities, it can be voltage or current. That means all these parameters, physical parameters, they are converted into these electrical quantities, voltage or current. Okay. Now these are processed further. That is what is a signal. So a signal means here it is an electrical signal basically. Let us see some examples of this. I have shown here 3 signals. On the top I have shown a sine wave with certain frequency. This is x-axis is time, y-axis is the voltage as a function of time, because as time changes, the voltage is changing like this. Periodically it is changing, sinusoidally it is changing. It is a very popular signal in case of physics also, because when we say transversal waves, and let us take a string under tension. You have tied a string to 2 ends and you just touch on that one. Okay, you just blow on that one. I mean with your nail. Okay, what happens? The string will move like this. Okay, that is nothing but transversal vibrations. So those things, if you can record the displacement there, they just look like a sine wave. Okay. And similarly, if you take a pendulum, so pendulum initially just leave it, take it here and leave it. It comes here to the neutral point. It goes this side, left. It reaches there again. It comes back. Like it will be oscillating like this. What it means is this simple harmonic motion we call in physics, and this motion, displacement from the center neutral position, if you convert it into electrical signal, it is nothing but a sine wave basically. So that is how this is sine wave is very popular signal, basic signal, which you will study much deeper in the coming classes. Okay. Now second signal is a triangular signal. What is happening here is, again, it is a function of time here, and V of t, voltage is changing with time. It is linearly increasing to certain value. Here, some value, let us say 1 volt here. Again, it is decreasing to 0 volts. Again, it is increasing to 1 volt, decreasing to 0. Like that cyclically. Periodically, the voltage is increasing to maximum value, again decreasing to the minimum value. This is called triangle wave. This is called a triangle wave. Okay. Both are periodic signals because the voltage is changing periodically with certain period. Okay. Now third one is I should say that it is a random signal basically, and this is the speech signal. Example of speech sample here. Here this is the word time. Actually time. When you say this is time. Okay. So like this. So this is the word, best example of electrical signal obtained by recording using the microphone of the word time. Okay. So 3 signals I have shown here, and let us move further to this. So now you know these are all real signals. Whatever I have shown as a real signal. Okay. Because in mathematics we have the complex numbers also. So they are not complex signals. They are real signals. Okay. First I am considering the real signals. So let us, because we have studied the inner product. I mean inner product in the sense, I think that is called dot product. Inner product, dot product, scalar product, all are same. Basically when you talk about vectors, we generally say scalar product or dot product. But when you talk about the signal, we call it as a inner product basically. Okay. Why it is inner products we will see. And the inner product, I can say it is a scalar product. You can also say here scalar product of 2 real signals, f of t and x of t. Here, what is the difference? Earlier in place of vector, I have taken only f. There was no t. Okay, f was not a function of t. Now it is a function of t. And here, x also is a function of t. So I am taking 2 functions here basically. Functions are nothing but signals. So what is function? Function means a dependent parameter, f, changing with time, changing with independent parameter time here. Okay, it can be any other parameter also. So t is independent parameter, f is dependent parameter. So as t changes, f is changing. Then this relation is called a function. This kind of changing over as a function of independent variable was not there in case of vectors. Okay, that is the difference. And here x of t, again same thing. T is independent parameter. As independent parameter t changes, the x also changes. Okay. So the f and t are functions, I should say. I can say in general mathematical functions, not vectors, mathematical functions. And these functions, the electronics engineer or electrical engineer can conveniently and safely call them as signals also. There are 2 signals or 2 functions, f of t and x of t. And over the interval t1, t2. So you are defining these functions over certain period t1 and t2. It may be, t1 may be in minus infinity or 0, t2 may be infinite. That is the latter. In general, if I take between any 2 finite time instants, between t1 and t2, I am defining these 2 functions. Okay. So now let us find the inner product of these 2 real functions. So what is here, what I am doing here, inner product? Integration f of x into x of x dt. So t is the dummy variable here. What I am doing, I am multiplying this function here. I am multiplying this function with the second function. So what I can say here is, I think better draw something here. I am drawing here for your convenience. So I am taking, so here first x-axis, second x-axis, third x-axis. Okay. So here I am plotting, let us say something like this, some signal. So I call it as f t. Okay. Second one is xt. And let us say this is something like this. Okay. Now I will multiply these two, f into x. I am skipping the independent variable. I am just multiplying these two. So what is happening here? So this part up to this part. So I can say these parts. So here I have some common. This is positive area. This is positive area. Okay. Then when I multiply, probably I will get something like this. This is what I guess. Okay. Something like this I will get. Then this is positive quantity. This is positive quantity because positive side, and this is negative side. Okay. Positive side and a negative side. Now when you multiply these two, I will get negative, correct? So all these things will become negative. So yeah, it will come down like this, and probably something like this, up to this. Okay. Yeah. Including this also you will get like this. So this is what I have, the negative area. This is the negative area. Okay. So this is, after I multiply these two, I have a product curve. This is first signal, first function, second function. This is the product function. So that is nothing but this is f of t into x of t. When I multiply these two, I will get the third waveform, and I am integrating. Integrating means I am finding the area under this curve. So here, this area and this area both are same. Probably the area may be very much small, very small, maybe 0.01, something like that. I don't know exactly. Okay, some example I am giving, maybe approximately 0.01, whatever it may be, very small quantity I will get here. Okay, so that is after integration. So what is the meaning of this one? I am multiplying two functions or signals. I am finding the area under the product curve. So that is nothing but cross energy. I can say inner product. I should say in terms of energy, because I have not introduced the energy term here. I don't use the word energy, but let us call it as inner product for the time being. So it is the inner product, and it is the integration of product of two functions with respect to t. And this I represent by these arrows. Okay. So this is notation is also used for the denoting the inner product. Okay. Now let us take the inner product of a real signal x of t with itself. Okay. So what I am doing here, with itself I am doing, and here I have x of t and x of t, x square of t. This is what I have. Okay. So this is, we can say that it is an energy. Why you say it is energy? Because x of t I told that it is a voltage or current. Voltage, if let us take it as a voltage, and a V square is power, and you are confining your waveforms to T1 and T2. There is a duration involved there. So T2 minus T1 is the time. So what I am doing, I am squaring, finding the power. V square means power. Okay, volt amperes basically, but V square by R, if I take, let us take resistance equal to 1 ohm, then what happens? V square by R. Okay, so it is a normalized power basically for 1 ohm resistance. So V square is nothing but power. Power into time, because T2 minus T1 period I am taking. That is called energy. So that is the reason this inner product can also be called as EX. Capital EX means the energy contained in the signal x of t. The inner product is nothing but the energy of the real signal x of t in the interval, because if the interval changes, again the energy will change. Okay, so that is the reason the inner product is exactly same as the energy of the signal. But whatever we have discussed so far is nothing but the real signal. Okay? Real signal means it is not a complex signal. There is no imaginary terms here mathematically. Okay? In fact, you cannot imagine, correct? All real world is real signals. Everything is real objects. So you cannot imagine. Only for the mathematical analysis purpose. So we consider the real and complex numbers basically. Okay. So otherwise everything in this world is real. Nothing is imaginary. Okay. Except something which you dream in night, or you imagine something. Okay. Correct. You imagine so many things which are not available in this world. You say that in the sky something is there. Okay. There are 7 seas. 7 lokas are there. There is one milk ocean. It's a milk ocean. Palasamudram. In Telugu it is called Palasamudram. Okay, nobody knows where it is, that Palasamudram. These are all imaginary things which have come out of your brain. Okay, so this is what is, but those kind of things science won't allow, and you have to base on your any science, any logic, anything, any logic presentation, discussion, and invention should be based on this world, real objects, real world. Correct? So that's why we consider this real world. But for mathematical convenience purpose, sometimes we go for complex signals. That we will see later. Okay? So now let us go to the complex signal. Same thing I told here. Complex. What is complex signal? What is complex quantity first? If I take A plus J B. A plus JB. Okay? A plus JB. So this A is real quantity, B is also real quantity, but A plus JB, if I express, this is called complex quantity. This is, which you know very popularly, this is real part, this is imaginary part. Okay, so this kind of things I am taking. When I say f of t is a complex quantity, what it means is f of t, I have a real FR, real quantity, plus J F imaginary quantity. I say that Ft, this must be T, because in the expression I have used T. So let me use the same T here also. So I have to erase this. Now I have to put T here. Real part of this function Fr, imaginary part of the function Fi, this is equal to the complex signal f of x. F of t. So f of t is the complex signal now. When I put minus here, fr minus j fi, I call it as a conjugate of f. Okay, conjugate of f. So that is what I have seen here. So first what I have taken the first function, complex function f of t, and second function x of t conjugated. That means I am conjugating. Star here represents the conjugation of this, because when I multiply two complex numbers, ultimately my world is real. My signals are real. I want to get the product as a real quantity. So if I multiply two complex numbers as it is, I won't get that. Correct? One complex quantity I have to convert into conjugate. Then when I multiply, after multiplication, I will get the real quantity. At least if the two vectors are same. I mean two functions are same. Correct? If two functions are same, if I take one as the conjugate and I multiply, I always get the real quantity. That is the purpose of conjugation. Okay? And so star is used for conjugation here. And same as it is, I am finding the inner product by multiplying these two and finding the area under the product curve. Okay? So that is what is. Inner product of a complex number is nothing but this is the inner product. And here, inner product of a complex signal with itself, same thing, x of t, x star of t, after conjugation, complex signal into multiplied by its conjugate. Then I will get the square of the magnitude of this. Correct? Square of the magnitude of this. So this is what you have. For example, if I take a plus b here, okay? Here if I take a plus b, what is that I will get? I want to find the magnitude of this complex number. What I will get? A square plus b square. And this is square root. This is what I will get. Okay. So let us call this as let us say some D. And this is nothing but magnitude of D. D is a complex number. Magnitude of D is square root of a square plus b square. Correct? Now when I want to get rid of this square root, so I have to square this. When I square this, it is a square plus. When I square this, what happens? Square this, it is nothing but a square plus b square. Correct? A square plus b square. So because I have got written of this square root. So that is the reason x modulus square I am taking, because here I have taken d modulus square. Similarly, here x of t modulus square I am taking. Okay. So this is, I can call it as a energy. See, though the function or signal x of t is complex, ultimately I got this as a real number. Correct? Energy is real. There is no meaning for complex energy. Energy is always real. And it is called the energy of the complex signal in the interval T1 and T2. Because once you have the energy, you should define the duration of that signal. Otherwise, you cannot use the word energy. Okay. Now, orthogonality of the signals. So, orthogonality of signals. Same thing. Take two real signals, f of t, x of t, and take the dot product like this. If the dot product equal to 0, you call this as, you say that these two signals or functions are orthogonal to each other. Correct? They are orthogonal to each other. That means if they are orthogonal, you cannot express one function as a function of another function. That means the part, if you see how much part of x is there in f? No, nothing. F is totally independent of x. X is not contained in f, or f is not contained in x. That is the meaning of that one. Totally uncorrelated, orthogonal. There is no similarity at all. Once I say f and x are orthogonal, what it means is there is absolutely no similarity between these two f and x signals. Okay, so that is the meaning of this one. And similarly, if there are two complex quantities, so naturally what is that the complex quantity? How you define? Yeah, it is here. So this is what f of t, x star of t equal to 0. Same thing, but dot product is with respect to one signal, dot product of one signal with the conjugate of the second signal in case of complex signals. Okay, that is the only difference. Otherwise, here also energy is EFX, means energy between these two. Here I should not say energy, because earlier I have shown EX, because x of t into x star of t, same signal. But here I'm comparing f of t with x of t, two different signals. So what I should say, at most, if at all you want to name it, you can put a nice word for that. That is cross energy. Okay. I'm using this one as a cross energy, and probably this may not have much relevance in the real world. Okay. So cross energy I can say. E of x. See, I will go back here. See here, this is energy or self energy. That means energy contained in the same signal x of t. Okay. And this is cross energy between the two different signals. So with that notation, I think cross energy is reasonable to use. Okay. Cross energy. Okay. So thank you very much for your patience, and this topic I will take in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.